Today I'm going to be talking about directed expander decomposition / gardening. And this is joint work with my advisor Jason and George. Okay. So since this talk is about expander decompositions, I want to start by just saying informally what an expander decomposition is. So an expander decomposition is just a partition of a graph into expanders where there's sort of few intercluster edges between them. For now, expanders are just well-connected graphs. I'll formally define this later. And here's a picture of an expander decomposition. So the graph is split into components V1 through V5. They're colored orange here to mean that they're expanders. I'll use orange for expanders in this talk. And there's sort of few intercluster edges between them marked in red there. Okay. Before I get into the details of my work, I want to try and convince you that expander decompositions are useful. So let me just say some applications in graph algorithms. So they were first popularized by the linear time Fleischmann solver, this Fleischmann in time, and then with the Godot prize. More recent application is this near-linear time exact max flow algorithm. An even more recent application is this near-linear time deterministic min cut, where they use expander decompositions to de-randomize the algorithm. But these are all about undirected graphs. I'm focusing on directed expander decompositions in this talk, which are much newer. They were only introduced in 2020 to study dynamic graph algorithm problems on directed graphs. And they found some home since then. I think the most interesting home is this almost linear time, or on the order of n squared up to log factors, augmenting path-based max flow algorithm, which if you've heard of the classical push relabel algorithm, this is just that algorithm, but you strengthen it with hints from directed expander decompositions. And somehow just like this classical algorithm plus these hints from directed expander decompositions gives you an optimal algorithm on dense graphs. My goal in this talk, I hope that those applications of expander decompositions convince you that expander decompositions are useful. And my goal in this talk is just to explain some of the key expander decomposition techniques and intuition, and using a gardening analogy. So I'll start with undirected graphs, and I'll try and tell you how this becomes difficult on directed graphs and how to maybe try and extend it. So throughout this talk, we're gardeners. And you're given this simple task. You have an unkempt hedge, like these ones are inspiration from the English countryside. And your goal is to apply typical gardening operations to the hedge. You cut, you graft, you trim the hedge, and you want to turn it into a nice, neat row of bushes. So the unkempt hedge at the beginning is like an arbitrary graph. And at the end, the neat row of bushes is like the expanded decomposition. Okay, so this is, if you ever get lost at any point in this talk, just think back to this gardening problem, which is what we're trying to solve. Okay, to say it again, with some more pictures. We start with the messy hedge. We cut it up into messy but separated shrubs, and then trim it up a little bit more. It turns it into this neat row of bushes. So that's what we're trying to do. So let me get into some of the technical details. Okay, so the first thing I want to say, I promised that I would actually define what an expander is. And we're going to give two definitions of expanders, because they are both useful for this line of work. Okay, so the first definition is a cut-based definition of expansion, which is that a graph is a phi expander if it has no phi sparse cuts. What's a phi sparse cut? Well, it's just a cut in the graph where there are few edges crossing the cut, the edges in red there, relative to the number of edges on either side of the cut. Or more formally in math, a subset of the vertices is a phi sparse cut if it satisfies this equation. So the left-hand side is this number of edges crossing the cut in the small direction of the cut. And on the right-hand side, it's this parameter phi times the number of edges incident to the small side of the cut. So it literally is just there are a few edges crossing the cut relative to the number of edges touching the smaller side of the cut. Okay, and something when I started thinking about expander decompositions which confused me was this parameter phi, so I want to say a little more about it. So phi is just the quality of the expansion. It's something which is less than 1, And the bigger the phi, like closer to 1, the better an expander. And for the purposes of this talk, we should think of phi as like 1 over polylog n. That's like the right regime for applications. Okay, so now I'm going to give another way to think about expanders, which is based on flow. So let me just say a little bit about intuitively what flow is first. So for this, we need weights on our edges in the graph. So it's like a capacitated graph. The capacities are weights. And we want to think of the graph as a sort of pipe network. What do I mean by that? So the graph, the edges are pipes, and I've colored some of the vertices. So the vertices colored red, they're like faucets. They're sending water into the pipe network. And the ones that are colored blue are like drains, they let water drain out of the pipe network. And, you know, opening all the faucets and letting the water flow, there's some notion of like congestion of the pipes. So like if the water could just flow from the faucets straight out the drains, there'd be like no congestion. But the congestion is like, how much do we have to scale up the width of the pipe so it could just flow straight through? And we can make this formal. Let me say what a demand is first. So I said we colored the vertices of the graph to make them faucets and drains. So these colors come from some function called the demand function. And negative demand is like making it a faucet. Positive demand is like making it a drain. And they have to sum to 0, so like it's actually possible to send the water through the network. This word demand is somewhat intuitive. Like the vertex is demanding to have the net flow into it be negative, as in it wants to send net flow out. Or the vertex is demanding that it has net flow into it being positive, so it wants to like drain water from the network. And then I say that a function on the edges is a flow if for all the vertices, and it's just a flow if it's a function on the vertices, but I say it routes some demand if the net flow into any vertex is equal to the demand. So that means like if you sum up the amount of flow on the edges going in and subtract the amount of flow on the edges going out, it equals the demand on that vertex. Okay, lastly, the formal definition of congestion is just the maximum of the ratio of the flow on an edge over its capacity. It's like if you've seen flow before, this might be unfamiliar because like sometimes you think about flow and there's like strict capacity constraints. Like you can't put more flow than the capacity of an edge. Here it's not a strict constraint, I'm just measuring how much we violate these constraints by that congestion. Okay. And we need that to think about expansion. Because yes?
Do you have signs on here? I think what you define is undirected congestion.
Wait. No, this is still right.
Well, so first of all, CE can be negative.
No, okay, I guess I didn't explicitly say, but it should be positive.
And also FE could be negative in the direction, in the opposite direction.
Yeah. There's an absolute value there.
So if the absolute value is, why is the direction?
Negative demand on an undirected edge, or negative flow on an undirected edge is like sending it backwards, but I guess it shouldn't be negative on a directed graph.
Okay, but you also need FE greater or equal to 0, and both FE and CE greater or equal to 0.
Sure. Okay. Yeah, so a graph is a phi expander if for all the demands, where the demand on any vertex is at most the degree of the vertex, you can route those demands with congestion at most 1 over phi in the graph. It's like there exists a flow which routes it, and the congestion of that flow is at most 1 over phi. Every time I use this definition in the talk, I'll restate it so you don't have to memorize it, but intuitively, it's like for any cut in the graph, if you color all the vertices on one side red and the other side blue, so they're like faucets on one side and drains on the other, then the water should be able to flow from the faucets to the drains without incurring too much congestion. So there shouldn't be a cut where there's like very few edges crossing between all the faucets and the drains, because that would mean you can't route it with low congestion. It's like this is an example of something that shouldn't happen in an expander.
I have 2 quick questions. So one is like this demands, like we're just thinking, okay, sorry, I guess maybe you already said this, like the red one is corresponding to positive demand kind of. And yeah. Another question is, so what is the,
I guess.
Or negative, yeah.
Doesn't matter.
What is the capacities?
Okay, so for this example, I didn't sort of explicitly state capacities, but if you imagine that the capacities of the edges crossing the cut are small,
yeah.
So it's like low capacity relative to the amount of like the total amount of demand on the faucet side,
Yeah.
then like there's a lot of water that's trying to go through, but
Yeah.
these pipes are small.
Yeah.
So
So sorry,
you-
I was just asking, like, for this definition, which is probably equivalent to the other definition of expansion.
Indeed, yeah.
Then, like, what are the? This is like an expander with some demands, but then what is this? What are the capacities in this, like, in this statement?
Oh, I mean, okay, so the congestion implicitly is relative to the demands.
Oh, I
Or
see.
sorry, relative to the capacities. Okay. Yes?
The degree is the capacity, right? Like you need to redefine degree to be the capacity.
Yeah, so the degree in our, yeah, the degree should be the weighted degree. Yeah. So like, we've added weights to the edges, so now the degree of a vertex is the sum of the weighted, like the sum of the weights of its edges incident to it. Yeah?
Sorry to interrupt you, my goodness, but is the weight of the edges in or out? Like
Both,
in
both,
degree and out degree.
both.
So the degree is now defined to be the sum of in degree and out.
Exactly. Yeah, no, that's an important clarification, because I'm talking about directed things first. Good, yeah, so as Noah pointed out, it actually turns out these flow and cut-based definitions are equivalent for expansion, and we can go back and forth, and it is useful for us to go back and forth. And if you want to think about why that is in your head, it's just, if you know the Maxwellian cut theorem, it's just direct application of that. Okay, good. So in summary, what are expanders? A graph is a phi expander if one of the two equivalent definitions hold. It has no phi sparse cuts. Or the flow-based definition, which is like roughly speaking, for any cut, you should be able to put faucets on one side and drains on the other and flow between them without too high congestion. So there like has to be enough capacity of edges going between. Okay. So because I'm going to talk about directed graphs, there's an important non-example of an expander here, which is a DAG. The DAG, a directed acyclic graph, this is just a directed graph with no cycles. So if you have two different vertices in a DAG, say u and v, and u can reach v, v shouldn't be able to reach u because it would make a cycle, right? So actually this will immediately say that this graph is not an expander if it has two or more vertices. Because if I put like a faucet on v and a drain on u, you can't get the water from v to u. Like if you put no demand anywhere else. So you can't, it's not even that you can't route it with low congestion, you just can't route it. So these are important non-examples, like these are not expanders. And not only are they not expanders, any subgraph of a DAG is a DAG. Because like if you don't have a cycle, no subgraph of u has a cycle. So the only expander subgraphs of a DAG are singleton nodes. Okay, so they're like, we're gonna talk about expander decompositions in a second. These are like very bad for expander decompositions. Okay. So now I want to state a claim about expander decompositions, which is for any graph, it has a phi expander decomposition, say into parts v1 through vk, such that first, the components are expanders. Makes sense. And then second, there's some notion in which there are few intercluster edges in the decomposition. So I'll say more about the left-hand side of the inequality in a second, but first, the right-hand side, we should think of phi as like 1 over polylog n, right? And m is the number of edges. So this is like a small fraction of the number of total edges, which are crossing. But this, this sum I less than j of like the edges from vi to vj, and this isn't quite all the intercomponent edges. If it were undirected, it would be. But in the directed setting, it's kind of like there are few intercluster edges between these expander components if you allow first removing a DAG worth of intercluster edges. And because of that previous example of a DAG, you need this to have any hope of saying something like few intercluster edges. Because a DAG, every edge, in the expander decomposition, every edge will be an intercluster edge. Okay, so we wouldn't be able to say few. And this is to try and interpolate between like the undirected and directed notions of expander decomposition. Yeah?
Have you defined G, the square bracket?
No, I guess. I mean the induced subgraph. So that is the subgraph on vertex set vi, where you only keep the edges between vertices in vi.
That is still a weighted graph.
Yeah, it's still the, yeah. Okay, thanks for that. Good, okay, so I'm just claiming this thing exists, but actually there's a simple way to see that it exists. There's like a naive expander decomposition algorithm. You start with the trivial decomposition, you just have like one set, which is all the vertices in one part. Then, in each step, you just look at all the parts you currently have, you see if any of them have a phi sparse cut in them, if they do, split it by the sparse cut into like 2 parts, and just keep doing this until there's no phi sparse cuts left to find. So by the cut-based definition of expansion, which is not having phi sparse cuts, if you do this until there are no sparse cuts left, you'll get an expanded decomposition. And the reason there'll be few intercluster edges is, I'm not going to do this explicitly, but it's because the cuts you're cutting are sparse cuts. So there's a way to like charge them to the small side of the cut. And then you get that edge bound there. So just to see what this algorithm looks like, here's an animation. So we start with a graph, and we find some cut. This is the first sparse cut we find. When we find the sparse cut, I'm coloring these edges red, the intercluster edge, or like the cut edges, red and gray. So the red edges are going to count towards this intercluster edge bound. And the gray edges are going to count towards like the intercluster DAG of edges we remove. We'll set up the numbers of the components at the end so this actually works. But note like the gray edges are like the big direction of the cut and the red edges are the small direction. Okay, so you go through, you find another cut. These 2 components at the bottom, they no longer have any sparse cuts, so they're expanders. And you just like keep going. And at the end, you can assign these numbers to the parts so that all of the red edges are going up in number. So they're counted in the bound before. And the gray edges are going down in number. And because they're all going down in number, you can see they're actually forming a DAG. So like it is actually a DAG of like removed edges that we don't count. So that's what the algorithm is. Good. But it's like not at all obvious that you can do this efficiently. Because I said like you find 5 sparse cuts in each step. And it turns out sparse cuts are like hard to find. I'll talk about.
Also, if you have I see. Is this the entire goal? Like, if you have a DAG, then the only possible expanded decomposition is every vertex is by itself, right?
But in general, I just want to be able to do this fast.
I see. So you don't like that's acceptable.
It's acceptable because we can't get around it. And this is an important point. This changes how you can use directed expanded decompositions. They're not quite the same type of tool as undirected expanded decompositions.
Because like I guess in any graph, it is not the case that putting every vertex in its own singleton component is like a good directed expanded decomposition.
No, I guess it is. It's just there's lots of intercluster edges.
Yeah, like there's also good.
Yeah.
So, I mean, on top of this, right, you have ordering of the vertices. So like when you actually do find a sparse cut, how are you, I mean,
how are you getting the numbers? Is that what you're asking?
Yeah, how do you like order the sets out?
Oh, okay. So I can say that actually. So basically, I said I'm only counting edges towards like the small number intercluster edge bound if they go from small to large index, right? So every time I find a sparse cut, I'm just gonna make sure that like all the things on the, so let's go to the first sparse cut. These things are gonna be on one side, those things are on the other. I'm gonna make sure the index of all the vertices down here is bigger than the index of all the ones up there. And I can just ensure this and then like keep going. So at the end, you can see, like these are V4 and V5. So that means that like the only, like the edges which go up in number to them are from that like sparse cut I found.
Like, is it true you're just always refining a cluster? Like, is it true you're just always taking a cluster in your existing order and cutting it up?
Yes. And that's important for this order. Okay, good. So I said like, yeah, it's not obvious at all you could do this efficiently, but there's actually some really important work which manages to do exactly that. So there's this result of Cernak and Wong, which gets an expander decomposition efficiently with almost the same parameters as the naive algorithm. So like, if you look at, like, you get 5 expanders, the number of intercluster edges, you've lost like two log factors maybe. But the point is the running time is like n log to the 4th n over 5, while phi is like polylog n. This is like near linear time.
Wait, so sorry, should it say directed and unweighted?
No, okay, so this is important. Yeah, this is the prior work that manages to do it for undirected. So
it finds a directed expanded decomposition and undirected.
No. This stuff does it, okay, yeah, I should say. So there's work which does it in the undirected setting. We want to do it in the directed setting, but this is like the undirected baseline.
I see.
Okay, there is stuff that does it in the directed setting.
So they are not allowed to remove like intercluster DAG.
Yeah, there won't be if you view the edges as like bidirected, you won't. You also don't need to.
I see.
I guess.
But like that sum over I less than j is like now just
it's just
sum
all
over
of
I
the
doesn't
edges.
equal j because every edge is there twice, like in each direction.
Yeah. So yeah, exactly. I wrote it like that for consistency with the directed result. So like the directed result, so this is quite recent, but this is the precursor to our work, and this does quite well. I mean, you get near linear time, and you get only up to log factor loss in like the expansion and the number of intercluster edges. And this also works for weighted graphs. And just at like a very high level, what is this algorithm trying to do? It's sort of like a reduction from the directed setting to the undirected setting. So you add fake edges to your graph to sort of pretend it's undirected, and then later you prune them away in order to make it back into like a real like directed expanded decomposition. Or like restated a different way in terms of gardening, it's like you're used to like a very specific shape of the hedges that you work with, and if it doesn't look like that, you don't know what to do. So you kind of just super glue in twigs as you go to keep it looking like something you're used to, and at the end there's just like some random super glued twigs in there, so you have to cut them out. Yeah, so that's kind of what this algorithm is doing. But yeah, this was a nice result. So this is the direct precursor to our work, and like that's our work. And so we get better parameters, I guess, and in particular optimal dependence on this like expansion parameter. But I think like the more important aspect of our work is that on unweighted directed graphs, we match Serenark and Wang, which is like the unweighted, undirected expanded decomposition algorithm. So we kind of view our work as the way to implement Serenark and Wang, but in a directed setting. Yeah.
I thought that this overfee in the runtime shouldn't actually be necessary, right?
Oh, you mean there are algorithms? Yeah, that's true. You can get rid of the overfee. That is.
Yeah, I just mentioned it because you said.
But for, yeah, okay. I guess like Serenark and Wang can achieve 1 over phi. So to make it like comparable to Serenark and Wang, you don't need over like 2 of them. I guess that was the point.
You're saying that there are newer papers that don't have that?
You can get rid of the phi, at least in the undirected setting, using like approximate max flow. Yeah, that is true. Yeah. Cool. Okay. So let me go back to this gardening idea. So let me suggest a potential algorithm for splitting up the hedges. So step 1, you have this messy hedge, you just want to break it into pieces. Okay, so carefully cut it up into pieces, these like separated shrubs. Maybe a bunch of branches drop to the floor as you do. You graft back in these branches if need be. If you're not familiar with that word grafting, I'll say what that is in a second. And then, you have these separated shrubs. They're not quite cleaned up, so you trim them into nice bushes. So that goes from that top step to here. And actually this is our algorithm, where the hedge is like the initial graph, the shrub is like a near expander, and the bush is an expander. And I'll say what near expanders are. But what is grafting? So grafting is like a pretty cool gardening technique if you haven't heard of it. It's this gardening technique where you take parts of like 2 different plants, and you like attach them together so that they grow as like part of the same plant. And this is like the right intuition for what we actually do in grafting for our algorithm. Like there is a new keyword, which is grafting. Okay, they're stated in sort of mathy language. We're trying to emulate Serenark and Wang, but in the weighted and directed setting. So the first thing we do is we efficiently compute a near expanded decomposition. And to do this, we introduce a new like directed nonstop cut matching game, which I'll get to later. This is the step where we go from the messy hedge to like separated shrubs. They're not cleaned up, but they're separated. And the last thing we need to do is we need to actually turn the near expanders, like these shrubs, into real expanders. This is trimming. And to do this, we strengthen the trimming algorithm from the previous directed work to work well in the weighted setting. Okay, so before we start with like this messy hedge, and after we split it into these like separated bushes.
What does the fence represent in your algorithm?
That's a really philosophical question that I'm actually not qualified to answer. I wish I could really, but okay. So good. So like once we start thinking about expanded decompositions, one of the first like natural questions is like, if someone tells us like this is an expanded decomposition, how do we know that these like subgraphs are actually expanders? And this is a real issue because, as I alluded to earlier, the sparsest cut question of like finding a phi sparse cut in a graph, this is NP hard. And it's in fact like hard to approximate up to unique games conjecture up to any constant factor. It's like we need to address this if we can get anywhere. Yeah.
I thought you had like log factors in your approximation.
We do, and that's important. Like
So
this
this
is why the
is
naive
just
algorithm.
an
This is just to
ARB.
say why the naive algorithm is slow. Like we have to get around this issue. We need to be able to tell if expanders are expanders efficiently, and we can't do that like exactly. So you'll lose. Like if you say it's an expander, you can't say exactly that it's an expander with the same parameter they asked about. You lose something in that parameter to do it efficiently. Does that? I'll talk about this more with cut matching. Yeah.
Wasn't there a paper by Max and Co that just says like for undirected, this is for undirected graph, but undirected graph, wasn't there a paper by Max and Co that says like an evening roughly works?
I'm not sure what that means.
Oh, there was
the
a
naive
paper
thing, meaning like the naive algorithm.
Like just like run sparse cut enough times. Like there was a kind of a paper by Max and Co that says like something of that.
But like approximate sparses cut?
yeah, just run sparse cut.
Oh, but I guess then you're not exactly like looking for. I guess it doesn't necessarily contradict that like this is a hard thing we need to get around because if you're solving it approximately, then that is sort of a way to get around it. I guess all I'm trying to say here is like, it's not given a graph and someone tells you it's a phi expander. You can't just say, oh, I'm going to look for all the phi sparse if there's a phi sparse cut. You have to get around that somehow. And I want to build intuition towards like how you might get around that. Okay, so like one idea is to certify that a graph is an expander using known expanders. So like high level idea is a graph is an expander if you could embed an expander into it. So let me say some stuff related to this. So suppose we have a known expander H, known phi expander, and we have some graph G which we want to say is an expander. And it has two extra properties I need to point out. H and G are on the same set of vertices there, B. And I'm also assuming that the degree of each vertex in G is less than or equal to the corresponding vertex in H. Okay. And then the last thing we need is I said something about embedding, so we need to be able to embed the graph H into G somehow. And that's what pi does. So we take edges in H and we embed them into paths in G between the same endpoints. So that looks something like this. So like H is our known expander, you have some edge UV, pi takes that edge and maps it to the path between them.
So we should think of it as like G is a sparser graph that somehow retains like the connectivity structure of H or something like that.
Yeah, and so the reason why the degree thing is like kind of weird is because it's going to be weighted.
No.
So it's kind of like there's loss in the weights in the degrees in H somehow. Yeah, but yeah, like somehow you could fit H inside of G with some loss. Yeah.
I thought H and G should be the same size.
They're on the same set of vertices. Here I was just showing it like this is the main thing we're thinking about. That's like the small thing we want to, or the thing we already know about which we want to put in. But yes, they're on the same set of vertices. That is important. Okay. So I want to formalize like this idea with this embedding lemma. And this is like at the core of all these expanded decomposition results to come, which is if this embedding pi has congestion kappa, and you can embed this known expander into G using pi, then you get that G is a phi over kappa expander. And what do I mean by congestion kappa? I just mean like the embedding doesn't overuse edges in G. Like it only uses it among all the paths in the embedding, like at most kappa times its capacity. Okay. And I think it's actually instructive to prove this embedding lemma because it's just a nice application of the flow-based definition of expansion. So recall this is the flow-based definition of expansion. We need to take a demand on G where it's at most the degree everywhere. Like the demand on a vertex is at most the degree of a vertex, and we need to route it in G with congestion 1 over phi. So like take such a demand. The first step we can do is, okay, we don't know how to route it in G yet, but note, this is also a demand on H. right? Because they have the same set of vertices, and the degree of G is most of the degree of H everywhere. And H is an expander, so you can actually route it in H with congestion 1/5. And the last thing is we need to route it in G somehow, so you take this routing in H and you just like embed it back into G using the embedding pi. So every time you use an edge in the routing in H, you just use the corresponding path, like the embedding of that edge in G.
Like the sum of the.
Yeah, like you stack them all on top of each other. And like this will incur an extra kappa congestion because like pi overuses edges by like a factor of kappa. But you still get to certify that G is a phi over kappa expander. Like this is pretty nice. If you take a known expander, you can embed it into a graph you wanna study, and then you can certify that that new graph is an expander as well. And this is kind of a simple idea, but it turns out it's like really useful in making expander decompositions efficient. Okay. So in particular, this is what we're going to talk about next. So the cut matching game gives us, it's like a really important result in this area and other areas. But this gives us a way to implement the like search for a sparse cut if it exists part of the naive algorithm. Because the cut matching gives you an efficient algorithm with these final guarantees. So either we find a phi sparse cut, or if we don't find a phi sparse cut, at the end we certify expansion of the graph G. And we certify expansion using the embedding lemma. So we find like a constant expander and we embed it into the graph we want to study. And it's actually like a pretty simple algorithm too. You just repeat like log squared n rounds of randomly split the graph into two parts, and then try and embed a matching between those parts with low congestion. If you can successfully do this, great. If you fail, you end up finding a sparse cut and you output the first case. And this is, it's not obvious why that is, but it's because you can implement this with like a flow routine or something. Okay, so I want to say, like it's probably still not obvious given this relatively simple algorithm, why on earth, if you don't find sparse cuts, at the end you'll certify expansion, but I'm going to talk about that now. Yeah, Richard?
What do you mean by the random?
Yeah, I specifically didn't say, because I'm trying to avoid the technical detail, but it's like, it's not that complicated, but it is like,
It's not uniform random.
it's not uniform random. It's not uniform random. And it's like, yeah, I mean, it's important that you select it randomly in a different way each round. It's not going to work otherwise. So it needs to be like adaptively random. But yeah, randomly in some smart way. But I'll talk about how we want to do it too. Okay, but like, if you're not finding a sparse cut, I want to say like, why could we expect to be making progress towards certifying expansion? So here's a thought experiment. Okay, for this, let's assume that the graph is deregular. So all the vertices have d edges coming up. And I want to suppose that for each vertex in the graph, you have d units of its unique flow commodity on it. So what does this mean? Before, when I talked about flow, there was just like water in the pipe network. For multi-commodity, it's like we're flowing around a salad dressing through the pipe network. So there's like a bunch of different components. You have like oil, water, mustard. They don't quite mix, but they're all flowing around at the same time. Okay, so like each vertex has its unique flow commodity. So one has oil, one has water, one has mustard, whatever. Okay.
You probably shouldn't have mustard, otherwise
Mustard's probably not going to flow very well.
Yeah.
But
Yeah.
anyway, yeah, it's like liquids of different density, whatever. Like, okay, good. And the intuition here is like, well, if there's a way to start with it all like separated and maybe mix up all the salad dressing like really well without like too much congestion in the way it's being mixed, like you're flowing it around to do this, so mix it up without too much congestion, and you can send like the commodities everywhere. It sort of gives you a way to route any demand on that vertex. Like it tells you could send, there's a way to like mix it up so you could send its demand anywhere in the graph. So like take that flow path to send it there. Like there's a formal version of this, which is, here's a claim, which is actually secretly a variant of the embedding lemma I stated before, which is just, suppose there's a multi-commodity flow with total congestion kappa, where every vertex receives d over n units of the commodities of every other vertex, I guess like including itself. If you can do that, then you actually certify that the graph is a 1/kappa expander. So like the point is, this variant of the embedding lemma gives us a goal to strive towards when we're like not finding cuts. So like somehow each of these matching steps in the cut matching game should help us build towards mixing up the commodities. That's how we want to design them. Oops. Yeah, this is our new goal. Okay, so maybe it's still not obvious why like matching steps help with this, but let me say why. So like, what does a matching step look like? You know, you find matchings between vertices, and these matchings are actually going to give us a way to make progress towards mixing up the commodities in the graph. So like, suppose U and V are matched. So in this picture, V had previously like sent out its I don't know, maybe oil, various places in the graph. U had maybe as water, and it sent out its commodity various places in the graphs, like these green paths. And the matching step gives you a flow path between the two. So we can make progress towards U and V sending their commodities more places by the following idea. So maybe V sends half as much of its commodity to the places it sent before. And the other half, it sends along the blue path to U, and then sends along U's flow paths. And U does the same thing, sends half as much as before to where it sent it, and the other half to V and along V's paths. So like this picture can change to this. So like U sends some to V, and then from V, and half as much to the places before. So like that. And so if they were sending to really different places, this makes a lot of progress towards like mixing up all the commodities in the graph. And that's like the intuition for the matching step. If U and V are matched, we can sort of average the places where they send all their commodities, so making progress towards mixing it all up really well. And we make the most progress if we match things that are like sending their commodities to very different places. And that's what the cut step does. So this is like what Richard was alluding to actually. You need to design the cut step not to just be uniformly random, but so that actually it's random in such a way that it guarantees that you're matching things that are like sending it to quite different places. This is important. Okay, so that's the cut matching game. And with this design of the cut and the matching steps, this embedding or mixing lemma will imply that after log squared n rounds, if you didn't find any sparse cuts in matching steps, like they all succeeded, you actually certify that the graph is an expander. Okay. So again, this is the result we get. You can do this efficiently, so this is really nice. And this allows you to implement the naive algorithm efficiently. But it's still not like near linear time. And the reason is, if you find a sparse cut, it might be like really unbalanced. You might cut out like one vertex. Or restated, you might, you're going through your hedge algorithm, you look for a problem, you cut off one leaf. You cut off one leaf, and you just keep doing that one leaf at a time, it takes forever. Okay, so you lose a factor of n in the recursion depth here. Okay, so this gives us a slow but efficient expander decomposition algorithm. So how do we make this faster? So Serenurk and Wong use something called the non-stop cut matching game here. So the idea is that when we find a sparse cut, you don't necessarily just want to stop. Because right, if you cut out like one leaf, you're taking forever. So they only really want to terminate on balanced sparse cuts. So what does this mean? It's like you find a cut, you match across it. You find a cut, and you tried to match across it, but now you found a sparse cut there. You weren't able to actually match across the cut. So like, here's this sparse cut. So in the old algorithm, you would just cut that out, stop, and recurse on either side. But for the non-stop cut matching game, you cut it out if it's sufficiently small and keep going on the remaining vertices. And so like, if you do this, you're not gonna quite certify the same notion of expansion. In particular, like some of the flow paths from previous matching steps, they might leave the component we're still working on. And if they do that, you're not, like, you use these flow paths to certify expansion somehow. So it's some weaker notion of expansion. It's actually something called phi near expansion. And the definition is like exactly from that picture. A subgraph of a graph is a phi near expander in that graph. If you satisfy like the normal flow-based definition of expansion, except you're allowed to route in the whole graph, not just the subgraph. Okay. So like this is the step where instead of partitioning straight into messy shrub or into like the nice bushes, we have to go first to like messy shrubs and then clean them up. The shrubs are the near expanders. Okay. That's all to say. Like this is all the inspiration for the techniques in our work. I want to say, and this is what we exactly try and do, but there's lots of complications that arise in the directed setting.
Okay, so everything you just talked about is only for undirected graphs.
All of these ideas, there's sort of subtle things which break for directed. I'm going to point out a few of them, and these are the kinds of things we need to address in our work.
Does the KRV thing work for directed graphs?
Or KRV does,
Okay.
actually. But when you try and non-stopify it,
I see.
that wasn't known before our
I
work.
see. So you could do, as you said, like you could do what they're doing, but you might just get every graph by itself. And so now the challenge is like
So you
every
actually,
vertex by itself.
you can do KRV.
Yeah.
The issue is you might find sparse cuts that are like tiny, like
Yeah,
singleton.
yeah.
Yeah, so it might take forever.
Yeah.
Yeah, exactly. So like the previous work gets around that with this like pretending it's undirected thing.
I see.
But we just try and like do the directed non-stop cut matching game, but in the directed setting. That's why I talked about it so much. Right. This is our main contribution. It's the directed non-stop cut matching game. So one complication that arises when you try and do this in the directed setting is that previously when we did a matching step and we succeeded in like matching, we had a guarantee that like the cut we matched across is not sparse. But here, you have to certify it in both directions. Like this cut is a sparse cut, but if you only try and match from the vertices on the left to the right, it looks like it's not sparse because you managed to embed the matching. So you actually have to check from the right to the left too in order to see it's a sparse cut. So you end up with 2 matching steps, or 2 flows per matching step. And like this seems like a simple change, but for some technical reasons, this actually ends up with us deleting nodes outside of sparse cuts. And this is a problem because if you delete nodes and they weren't deleted by removing a sparse cut, you can't just make them their own component in the decomposition because it's not a sparse cut, so there might be lots of edges crossing that cut. For example, let's see the algorithm if you just try and do this. It's like you find a cut, you delete some stuff, the gray part, and like if you just try and cut it out as its own component in the decomposition, you would add a lot of intercluster edges. And each round you do that. So you get something which looks like an expanded decomposition, except there's like these deleted chunks all over the place. So what do? Okay, this is why there's grafting. So this is a new technique we introduce. The implementation is actually not so hard, but what this post-processing step does is it takes these deleted chunks, the gray nodes from before, and it just tries to like graft them back into the near expanders they came from. Like, in a sense, they're like part of the same bush now, or whatever. If you succeed, great, they become like the same near expander. If you fail, you actually cut it out in a sparse cut, so you can recurse on either side. Does that answer your question, Richard?
Oh, sorry, by graphing, do you mean like you're like running more flows?
Yeah, so you implement this with like dynamic flow.
Which dynamic flow are you using?
Okay, in this I was talking about like unit flow, I think, but
This is a dynamic directed flow.
yeah. But it is okay. Unit flow will work for this. You can also iterate just using if you're allowing like max flow call times, you can run exact max flow. You actually won't be done in one iteration, but you can iterate and it'll work. So this one doesn't need like the full strength of dynamic, but it speeds it up by a log factor if you use it, so that's why I say that. So like this grafting step is the point at which you cut into shrubs, maybe you lost a bunch of branches on the ground. Instead of just leaving them, you try and like put them back into your various shrubs. You graft them back in. Okay. And again, here's a big picture of grafting. These twigs are from a different plant and the big branches are what you're grafting onto. This is like lowered. Okay, so the last thing I need to talk about is we only get a near expanded decomposition at this point. Like these are messy shrubs. They're not like nice pretty bushes. So how do we deal with that? We need to turn these near expanders into expanders. And the issue with them is like near expansion was defined as these flow paths that don't necessarily like stay in the right component anymore. So we have to reroute the flow paths somehow. If we can just like directly reroute them, then we'll certify expansion. So just to show this pictorially, we have some expander H. It certifies the expansion of like this yellow part, which is like a near expander now. But it certifies it by embedding these edges into like flow paths that leave the yellow part. Because it leaves it, it's a near expander. If it stayed in it for all of these embeddings, it would actually be an expander. So if we can reroute this flow path to like the purple path, we'd be good. And that's what trimming does. So Cernock and Wong can implement this with one max flow call using undirected graph, crucially using undirected graphs. The reason is, like, in the directed setting, their approach only certifies expansion in like one direction. For the directed setting, we need like 2 different demands corresponding to the 2 different directions to be simultaneously routable. And for this, we need like a dynamic flow algorithm. So in the previous work, they do this with something called, the previous directed work, they use push-pull relabel. We strengthen this for weighted graphs with something called regularized push-pull relabel. Yeah. Okay, so this is the step where we take these shrubs and we actually clean them up. We turn them into the photo-ready bushes. This is the end of our decomposition. Okay, so to conclude, in this work we gave the first, okay, I guess we can test this 5 thing. But we give a near linear time algorithm for directed expanded decompositions for weighted graphs. And along the way, and I think more importantly than that, we introduce all these new tools. So we introduced the directed nonstop cut matching game, expander grafting, which has already been used in follow-up work, regularized push-pull relabel. And probably the most important avenue for these like directed expander compositions is find more places where this structure of like having a DAG base case is not the end of the world. There are some applications to max flow that do exist, but this is a significant difference to the undirected setting. But in any case, happy gardening, and I'm happy to take any questions.